Hello all, I'm Shakti Veerasinghe and I'm a PhD student at the School of Information Technology at Deakin University. Today I'm presenting our work on the topic estimating the lifetime of transient context for adaptive caching in IoT applications with my supervisors Professor Agadi, Professor Singh, Dr. Alexei and Dr. Amin. We'll first take a look at the problem. Big IoT data is central to deriving context, but there are two problems it poses for a modern context management platform. First, IoT contexts are various and heterogeneous that lacks any clear pattern. Secondly, and most importantly, contexts are transient, it changes against time. So when considering adaptive caching as an option to optimize for context query processing, context refreshing is a significant aspect to deliver valid, accurate context that is consistent with the real world. These are matters of quality of context, but frequent refreshing is expensive, process intensive, and sometimes cause delays in response, so which are affecting the overall quality of service. It is therefore clear efficiency of context refreshing depends on the knowledge of the lifetime of IoT context data as we define here. Despite this transiency, various work assume lifetime to be constant, often attributing lifetime with sampling rates. TTL is a similar notion used in literature for adaptive caching in ICNs and CDNs. The problem here are that variations of natural properties that IoT devices like sensors measure are random. The value of this data is also lost non-linearly, which makes problem non-trivial to develop an ideal context refreshing strategy that theoretically results in the minimum number of retrieval operations, but still maintaining the highest quality of context. So basically, that is if refreshing could be synchronized with the lifetime of sense data. So in this work, we try to investigate an adaptive mechanism to refresh cached context data cost efficiently by estimating the actual lifetime of context attributes. So for this, we developed and evaluated two adaptive retrieval strategies, reactive and full coverage, which benchmarked against the non-adaptive strategy. The non-adaptive retrieval could be viewed the redirect mode or retrieving for each context query. It's cache oblivious but guarantees maximum freshness of data. But it could also be useful if cost of transmission is significantly lesser than the cost of caching. Reactive retrieval retrieves context only if the cached context is no longer fresh at a given freshness level. So the delay until this next retrieval is subject to the current estimated lifetime of the data. In other words, it's the gradient or the gradient loss function that adapts here. Similar is the next strategy, but full coverage is a proactive retrieval strategy that guarantees retrieval at the end of the currently estimated expiry period based on estimated lifetime. So it's always results in a hit rate of 1. But the problem here is that there is no guarantee to the quality of context, but it is useful when the cost of caching is smaller than the retrieval cost. So considering we use a rolling window within which the metrics are observed and the lifetime is inferred, there are three factors affecting this process: the window size, freshness threshold, and the channel reliability. So based on those, we make the following three hypotheses in the slide. Here, learning rate is the metric used to denote how fast the strategy is able to converge the inferred lifetime to the actual lifetime. So in this work, we develop comprehensive mathematical models to infer the lifetime of IoT context data based on a moving average method. In the paper, we present models to infer lifetime, estimate the learning rate, time between consecutive retrievals, expected number of context queries that could be served through cache, the delay rate, and the invalid rate for each of the retrieval strategies that we discuss. We present our models under two circumstances. Firstly, when lifetime is longer than the window size, and secondly, when lifetime is small enough that several values could be retrieved during a window. I don't intend to present them in this presentation due to time constraints, but we attach an appendix to our paper as well for the interest of readers to refer to the proofs of our models. We also measure cost efficiency. We define this gain or loss model for a single SLA scenario. So by single SLA, we refer to an agreement between the context management platform and the consumer on acceptable quality and performance matrices such as freshness, response time, and monetary aspects like price for a context query response and a penalty if the SLA is violated. For example, when the response time or the freshness is not met, then there will be a penalty that is incurred to the CMP. We also introduce an abstract cost, the loss of reliability, as a function of invalid rate and penalty for responding with invalid context data. So we developed our test bed for evaluation using Python. It comprised of two components, the context management platform prototype and a car park simulator. The context queries were generated using Apache JMeter, and the CMP prototype contains a limited size first in first out cache memory. The car park simulator is configurable to vary lifetime and the number of available slots to conform to a normal distribution, or to be consistent, or not to vary at all. In evaluation, we first tested the response time. So the response time improvement was approximately 97% in our setup compared to non-adaptive retrieval. So this is mainly for full coverage, and it was consistent because it was always responding to the cache. But in figure 5, we find an interesting observation using reactive retrieval over a range of freshness thresholds. As we show, it conforms to a third order polynomial function, and we mark this area to minimize the response time. Ideally, this range is the freshness threshold, is what we like to refer to as ideal for achieving our efficiency goals. So we will later also show further evidence to this as well. In the next figure, we show the variation of hit rate and the validity of responded context measured using the root mean square deviation of value and invalid rate. Quality of context gradually increases with the freshness threshold, but the hit rate decreases for the reactive strategy. So these two in combined proves our second hypothesis that we stated before. But when we look at the ratio of deviation of the inferred lifetime against the actual lifetime, which also shows some convexity that minimizes within the same range of freshness threshold that we identified before. So this is interesting because our main objective itself is to synchronize the gap between two retrievals as much as with the actual lifetime to maximize cost efficiency. The other factor is in our discussion is the learning rate. So in our models, we state the linearity and sometimes the exponentialness of converging to the actual lifetime. So as in figure 8, we tested convergence against freshness thresholds, and smaller thresholds converge faster. This conforms to our models, but we have to note that smaller thresholds results in overestimations of lifetime, increasing the invalid rate, especially with the reactive strategy. The other problem is the longer time that these strategies take to settle at the inferred lifetime. For instance, you may see it in figure 9 using the reactive strategy. The gap times need to minimize to reduce the number of cycles it used to settle down as well. This is in contrast to why the full coverage does not show any cycles. However, as per figure 11, full coverage inferred the lifetime most accurately and at the least time, followed by non-adaptive and reactive strategies. We can prove these behaviors using our models, as we have shown here for the non-adaptive strategy. Finally, we tested out how inferred lifetime is affected by noise. As we hypothesized, the number of retrievals positively correlated to noise, increasing the cost of retrievals and reducing the quality of context responded for queries through cache overall. Interestingly, however, we see that the deviation of inferred lifetime against the actual life reduced. It is a result of the higher number of retrievals, but contradicts with why quality reduced. This is characteristic with noise. So what happens is when noise manipulates the values randomly, the retrieval process goes out of sync with the sampling process, although the gap time is similar. Overall, the proactive retrieval strategy, the full coverage, was most profitable in terms of the gain or loss. It is the same considering the monetary profitability as well. Non-adaptive strategy is clearly unprofitable monetarily, which clearly signifies the importance of caching and adaptation for context management platforms. However, one of the important aspects that we cannot forget is the quality of context that full coverage is most prone to, despite the profitability. In that sense, we have to refer back to the features of reactive strategy, the minimization range of freshness thresholds, the lower ratio of deviation of inferred lifetime compared to the full coverage that could be seen as advantages over the full coverage strategy. But as there were disadvantages in terms of time to settle up at the actual lifetime, longer convergence time, and underestimating the consistent lifetime, full coverage could still be viewed more suitable for context retrieval and refreshing. So in conclusion, we make the following remarks in the slide. Overall, we prove all our three hypotheses. We defined what are infeasible SLAs and identified an optimal range of freshness thresholds for a CMP to achieve our quality, cost, and performance objectives. Adaptive retrieval was clearly seen to be profitable compared to non-adaptive retrieving, also signifying the importance of caching and adaptation in responding to context queries efficiently, which we'll be working on in our research further. So thank you very much.